Okay, great
I'll
stuff.
say a couple of things.
All right.
Welcome,
So, yep. Okay, Perry, go ahead. Go ahead.
welcome everybody to another Cloud and DevOps Babies programming-based session. This is a second session programming related from Andrew Elston of Liquid from Africa. I hope you enjoyed the last two sessions. The first one was introducing fundamentals of programming. Last week's very engaging session was around Golang, and I hope that you all took away some valuable kind of insights from that. This week we're kind of like expanding upon that and taking it to the next level. So with that, I'm going to stop speaking, hand over across to Andrew Alston, and let's get to the good stuff.
Yeah, okay. So firstly, thank you very much for having me once again, and to all the people on the stream. I see that we have a couple of people watching on YouTube, a couple of people watching on Facebook. We have lots of people on the Zoom session. Just as a note, I take questions as they come, and I can see those questions, so I will be responding to them as they come in. I will say that we do seem to have a slight bit of a lag between the various streams, so bear with me if you ask a question and it takes a little while for me to respond. I may have to go back a little bit. So, first session that we did last week, we talked about some of the basics of Golang, and we ended the call with a challenge from Joe. Thanks very much, Joe, to write something that could find prime numbers between a minimum and a maximum range. So I'd like to see in the chats, the various chats, who attempted this and how did you find it? You can go on, if you're on the Zoom call, you're welcome to go voice. Otherwise, on Facebook or YouTube, you can respond in the chat. How did you find it? What was difficult, etc. Before I start working through the ways that I've done this in two separate ways.
Anyone from the group who would like to go first?
I think they're all scared to admit they tried.
I think we might be able to pick somebody if they don't volunteer.
Yes, I will. I'm going to do that.
Joe Virus.
Okay, I count 1, 2, 3. Who is starting?
Joe's starting. Where's your attempt, Joe?
I'm still testing, Andrew.
Okay. I know that we've had a couple of people that did try this. Saki, yes, in response to your question in the chat, this is open to everybody. So let's start with, okay, I cannot pronounce names. So the last name in the chat said they were finding difficulties on the inner loop. So we'll talk about that. Did anybody manage to actually successfully produce code to find prime numbers? I know at least one person did, so speak up.
Yeah, I did. You know I did, Andrew.
I know you did, but so Simon, in your attempt, what did you find the most challenging? What did you find easy? How did you find the exercise?
The thing I found most challenging was when I sent you my first attempt and you told me to go away and try again.
Okay. Okay. So let's start.
So
go for it.
My first attempt was I had a look for a library that would find prime numbers. I came across a library called that's math big library, which has a routine called probably prime, and I used that. And I sent that to you, and you said, no, go away, do it again.
Okay, so let me just explain that. Guys, if we are learning something here, using a library function to produce the task where you're writing one line of code is cheating, and you're not going to learn very much from it. So while I applaud the initiative in finding the command in the library, I do not accept the answer. But what I'm going to talk about now is just to take a brief look at this before we move on to more interesting things as to how to solve this problem. Now, there's a GitHub link which I'm going to paste in both the chats, well, all three of the chats now, that contains all of the code that it has various examples for the challenges as we give them. It also has other stuff that we'll be discussing this week, and I'll keep adding to it as we go. So it'll probably run ahead of the classes as well, and you're free to work ahead on those things. But the code that is on my screen at the moment that you guys should be able to see is our first exercise in creating, well, finding prime numbers. And this is what I want to talk through. So the first thing I did here was I created a function. It's called find prime, and it takes a minimum and a maximum argument. So find prime numbers between this and this. Nice and simple. Then I created a Boolean variable. Now, this Boolean variable is used in this particular case to say that because we're going to be using two loops to do this, and you'll see it below, we need to be able to signal from the inner loop to the outer loop whether or not this number is a prime number so that we can actually do something with it. After
Hey,
that,
Andrew.
yes.
Hey, Andrew. What's a Boolean variable?
Good question. A Boolean variable is a variable that simply has two values, true or false. That's it. Imagine it like binary where you've got 0 and 1. So Boolean can be set to either true or it can be set to false. That's the only thing you can ever put into it. Make sense?
Absolutely, sir.
Great stuff. Then we have another variable, I called it res, short for result. That is a empty slice of integers. Basically, it's just an empty slice at the moment that I'm going to add my prime numbers to before I return them. You'll also note that this function has a return that allows me to return a slice of integers from the function to the calling routine. Then we get to actually starting to dig around and find some prime numbers. So what I've got here is I've got an outer loop first, and this outer loop is iterating through the numbers in the range that I've given. So from minimum to maximum. Every time I iterate through that, I start and say, by default, I'm going to assume that a number is a prime number. So I set the Boolean variable, which I've defined up here, to true. And then I start an inner loop. The inner loop is now to test whether or not the iteration that I'm on in the outer loop is actually a prime number. So I start and I say, start at 2, because if it's 1, well, it can't be 1. It needs to start as 2 if you're going to find a prime number. And I say start at 2, go to half of the number that is I'm currently on in my outer loop, so half of the iteration. The reason for that, well, if you're finding a prime number and that number is greater than half of the number, you're always going to get a remainder. It's an invalid calculation, basically. So go to half of the outer number, increment until I get there. Then I say, if I, which is the number in my outer loop, divided by j, whoops, sorry, I cut and pasted the wrong thing there. Hold on a sec. It helps if I'm not screwing with my mouse. So if I divided by the number in my inner loop is equal to 0, that percent will basically return the remainder of a division. So if I divided by j has no remainder, we know that this is not a prime number, because if it was a prime number, it would only be divisible by itself and 1. So we set that this is not a prime number, and then we break out of this inner loop. There's no point in continuing on the inner loop if we've already know that this is not a prime number. So this break command breaks out of this inner loop. Once we've broken out of this inner loop, which is all defined over there, we say is prime. If is prime, sorry, if is prime basically, is that true? If I wanted to test if this is false, I could do that, which would test it for false. I could also do that, which tests it for true. But since it's just true or false, I can leave out the equals true and just go if is prime. If I also wanted to test false, I could put an exclamation mark in front of it and simply negate it, which is basically the opposite of a true over there. But we want to know if it's true. So if it's true, then take the number from the outer loop and put it into my slice, which is defined over here. At that point, repeat this whole outer loop, which will repeat the inner loop, and it'll keep adding it. Finally, when it's finished going from minimum to maximum, return the resulting slice of numbers into the main function. So, has anybody got any questions there before I continue, either in the chat or on the Zoom session? No questions? Or have I lost you guys? I'm hearing silence.
No, we're here. All good on my side. No question at the moment.
Okay, good. Then, well, let me continue from there then. Now, what I did next is to take things a little bit further than just this prime routine, because there are a couple of things that I wanted to show you guys in this code. So we're going to take a look at my main function. This is the function where I'm calling to look for prime numbers. Firstly, I want to see how long this whole thing is taking. So I start off and I create a variable that is of type time.time. This is actually coming from the Golang internal time package, and it is simply a variable that represents a time value. So I'm defining that, and I'll use it in a little bit. Then I define 4 more variables. Now, these variables here are using an internal Golang package called Flag, and they're used for bringing in command line flags. So effectively what this says is, give me a command line flag called min, set its default value to 2 and describe it with that help section. Same thing for maximum. Those are both integers it's expecting. The next one is a Boolean flag, which can be true or false on the command line. That tells it I want to dump the list of prime numbers located, or I don't. The next one is a time execution. Again, do I want to dump this or don't I? That creates those variables. Now with the flag package, and I'll talk about importing the flag package in a second, I'll go back to the imports. Once I've defined those, the first thing that I've got to do is actually tell the code to parse my command line arguments. It's a really simple thing to do, flag.parse, bang. That will go and see if any of those things are set, and it'll fill in my variables. Just as a note before I continue on the imports, because remember I referred to importing packages, you'll see over here that I'm importing the flag package. I'm also importing the time package, which is where that time.startTime came from. It's also where the flags, the whole flags package is coming from. Those are both built-in packages, by the way, so you don't need to download anything extra for them. Then I get to an if statement. Now, there's something a little bit strange here, which I'm not going to go into great detail about at this point, because I think I'm going to do an entire session on pointers. But effectively, minimum, maximum, dump primes, and time execution are pointers. So to access them, I need to get at their base value. What is this thing pointing at? Which is why you will notice that I've got a star, an asterisk, in front of each of those variables. That simply tells me, give me the value of what is in there rather than the pointer. I hope that makes sense.
Send up some. She's been baking some Indian food.
Oh.
Sustenance.
It's on 3 platforms for me. Facebook.
Okay, so Perry, you got question?
No, I'm talking in the background and I should be on mute. Sorry for that.
No problem. Okay, so I just had a question in the channel, which I'm going to go back to quickly about on why prime is true is equal to is prime alone. So basically, if you've got an if something and it's a Boolean variable, then that equates to if is true. If you say if not is prime, that equates to is false. So by default with Booleans, if this is the equivalent to saying if this is true. Does that make sense to the person that asked the question?
Yeah, it makes sense. Thank you, Andrew.
Okay, perfect. So basically, as I was saying here, we dereference these pointers. I will talk about pointers later. For now, what you need to know is if you're using the flag package, any variable in there, to get their values, you've got to add the star in front of it to dereference the pointer. And I will talk about that later, but let's leave it at that for now. This says if minimum is greater than maximum, that would be invalid. Or if minimum is equal to maximum, because that's also kind of invalid for the purposes of our calculation, then print this line here. So print minimum in range must be smaller than the range maximum, and then print the flag defaults. And I'll show you when I compile this what that does in a second. Got another if statement that says if minimum is less than 2, print a message, print my flag defaults as well. In both cases, I simply return that quits the program. Then I test. Remember, I've got 2 Boolean flags on the command line, dump prime and time execution. I test whether or not that is set. So is prime, if is time execution is the same as saying is this set, then grab my start time. What is the time that this is starting? Just so that I've got it saved. Then I run my find prime routine, and then I say, if I am timing this, print a line here, which will tell me how long this took. And I'll show you when I run this in a second. Then after that if statement, I tell you how many primes I've got within the range. So I print that out. Then I say, if this dump primes is true, I'm going to print all the primes that I've got, and I loop through the result that I got up here, and I print each of the results. Now, let me show you what this actually looks like. It's going to expand this a little bit. If I run a dash help, the flag stuff fills in all of those values from those defaults that I set when I showed you the code earlier. To show you that again, it's printing these last sentences that I've got over here. If I run this thing and I actually specify numbers, so I'm going to say I've got a minimum of 2 and I want to find all prime numbers to 20. It tells me I've got 9 prime numbers between 2 and 20. At the moment, because my default on dump prime is false and default for timing is false, it's not acting on those. If, however, I tell it sorry. it now tells me that it took 0 seconds to find all the prime numbers. It's actually such a small value that it's not even showing it in milliseconds. It found 9, and those are the 9. There's the iteration loop from 0 through to 8. Those are the prime numbers. Any questions on that? Before I move on. And then the next question that I wanted to ask you guys is, do you want me to go through the more complex example, because that's more math than code? And in which case I'm going to ask a colleague of mine to step in and start talking. But if you want to, you've got a choice. We can go into more code, or we can go into the math behind the faster version. Which would you like?
I think, Andrew, one of the thing is we take two numbers and find out the execution speed of the Golang. Like in this case, it just executed in a fraction of not even a second.
Yeah, if I take a longer version of this, so I'm not going to dump all of them, but I'm going to tell it
Yeah.
to generate like, let's see, 6,000 of them took 4 milliseconds, right? If I take
Yeah.
this to 60,000, it's taking 310 milliseconds to find all of the prime numbers between 2 and 60,000. Now, without going through the code for the other one, what I am going to do is I'm going to show you what the other one looks like in terms of speed, because this gives you an idea about how much difference optimization can make. Let me just build this. So again, similar arguments, except this time I don't take a minimum. I'm just going from 2 going forward. If I run this and I go max of 60,000 and timing is true, on the faster version, that took 1 millisecond. So 300 times faster. And in fact, if I take this all the way up to, what is that? That's 6 million. Let's make it 60 million. If I run that on 60 million, it does it in half a second for 60 million.
Wow. This is this is like,
and the thing is there, it's not because of a code change. It's because in the one case, I'm using an algorithm that is designed to find prime numbers. And the code for all of that you can find in the GitHub repo. It's over here. I have commented it with fairly deep explanations of this. This code is very similar to code that I found online, with a slight difference in the fact that the code online was actually making an entire slice of Boolean variables which it was setting. I decided to skip that and use uint8s because it allowed me to skip a entire initialization loop in the beginning, which sped it up. But if you guys want the original, I can show you the difference afterwards. But my point here is, when you're writing code, you've got a choice. You can do it the easy way, or you can go and get a proper algorithm to do it. And if you can figure out how to write the code to do the correct algorithm, you are going to get performance benefits. Any other questions on that before we move on? Okay, so today what I want to do is, because I always said to you guys, I prefer to teach fundamentals. And so now we're going to look at some Golang code that talks to fundamentals. And we're going to talk about binary and binary mathematics within the context of Golang. And this gets quite interesting, actually, because in terms of the binary, there's a lot you can do. And It may take you a while to see the point of some of what I'm about to show you, but we'll get there. So bear with me. And if you've got questions and you don't understand anything, please stop me immediately, because if I lose you on this, it's going to be quite hard to kind of come back. All of this code is very, very heavily commented. It is all on the URL on the GitHub repo as well. So firstly, what I've got in this code is a series of functions that perform a series of operations. Technically speaking, I could just do the operation straight in line in code, but because I wanted to print out all of the results and show you what was happening here, I put this all in individual functions. So firstly, how many of you guys have worked with binary data or binary as in zeros and ones before, done any binary math, anything to that effect?
Anyone from the group? Rajesh from India? Have you done that anything in your day job?
Yeah, yes, Andrew. I worked with IP address scheming.
Okay, so you've done some stuff with binary and IPs. That's
Yes.
actually that'll help you, because when we start getting into the more advanced stuff later, you'll understand some of the application of this a little bit better. But
what about coming? So Andrew, what I'm doing is going around the group and literally taking out the names and finding out if they have done something like that. Kamil from Poland, have you done something like that so far?
Nope.
Okay, that's good. You will learn that from here. Let me see who else. Sadiq from India.
Hey Joe, I've done the IP addressing part.
But not the binary part.
I mean, like IP address to the binaries. So how the octets will get into it, I have done that.
Okay, sounds good. Let me ping somebody else. Okay, who is Pubaraj? Pubaraj. I'm sorry if I pronounce your name a bit different.
No problem, Joe. Just I'm learning. Still, I didn't start yet to start.
Okay, sounds good. All right. I think Simon is saying, let's see on the chat. Yes, he did. Okay.
Yeah,
So
I'm quite fortunate actually that my primary school teacher over 40 years ago, well, it'd be about 45 years ago probably, taught me how to count in binary and how to do math in binary.
You're not that old,
wow.
I'm well, no, maybe it's 42 years ago. I'm 50, so I was about 8 at the time that I learned binary.
So there you go, Andrew. That's the overall from the group.
Okay, so firstly, I did see a question that came in from one of our viewers on YouTube that asked me, what do I mean by binary data? In this particular case, what I'm referring to is the fact that a computer, a normal computer, stores everything in a series of zeros and ones. So if you've got a number, be it 5, 10, 20, whatever, it is effectively a series of zeros and ones that the computer then creates a full number out of. Computers typically store numbers when they're storing it in memory in bytes, so 8 bits at a time. Obviously, you've got 16-bit numbers, you've got 32-bit numbers. The larger the number, the more bits you need to make up that number. So the binary number system, we commonly nowadays think in terms of the decimal number system, which is a base 10 number system. Binary number system is a base 2 number system. We'll at some point start talking about hexadecimal, which is a base 16 number system. But for now, we'll stick with decimal and binary, which is being the base 2 number system. So now, within binary, when you take two numbers, you can add them and subtract them and do all sorts of things in decimal. In binary, there are a number of very specific operations that you can perform on one number versus another number. So what this does is show you what these operations are. So we start with what is called a logical AND. And what I'm going to do quickly is I'm just going to drop down and I'm going to comment out some of the stuff so that we can run this one at a time, and then we'll go through each example and I will compile this and run it. So if we look at a logical AND, which I'm going to pull up the code back up here again. A logical AND says I'm going to perform a logical AND and I passed 50 and 60 into that function. Now over here I'm printing those two numbers. Now you'll notice that I print this thing, that %2D by the way, says print the decimal number 1, but print it padded as if it were a 2-digit number. So I could say print 10D and it would, increase the padding between those two brackets over there. But print the number and print the binary. This 016B says pad this thing to 16 zeros, because otherwise, if I've got a binary number, it's going to chop off all the kind of zeros at the beginning of it. And to align this nicely and show you how this works, I wanted to print all 16 bits. So if I look at this, my number 50 is made up of that binary number there. Bunch of zeros, 1, 1, 0, 0, 1, 0. My second number is made up of a bunch of zeros, bunch of ones, 2 zeros. Then I do a logical AND together. Now what a logical AND says is if you've got a 0 and a 1 or a 0 and a 0, it comes out as 0. If you've got a 1 and a 1, it'll come out as 1. So that's what a logical AND does, and you can see it over here. At the beginning, 50 had a what we call the lowest order bit. So binary, you refer to highest order and lowest order. The highest order bit, which is bit 0, is basically the one that will change the number the most. Over here, this is all zeros. It comes out as 0. This is a 1 and a 0. It comes out as a 0. 0 and 1 comes out as a 0. It's only these two bits that survive. And you end up with a decimal number of 48 because of that calculation. Everybody following me? You will see the use of this later.
Yes, yes, I can, Andrew.
So all of you in the group, this is very important. If any one of you have any questions before we proceed, we can spend a lot of time from Andrew, but this is really an important concept if you want to understand. So if any one of you have a question, go ahead and ask. And if you want to repeat, Andrew would be very happy to repeat it. Yep, Rajesh, you have a question?
Yeah. So I understand the binary part. This is the there are logical and or functions are there in that binary. But in any general programming language, how binary is going to help improve either the performance of the program or where we normally use this binary concept in programming.
Okay. So Rajesh, we will come back to that question later.
Okay.
Which we will go through. At this stage, what I'm looking is there anyone from the group or from the other media where they did understood the binaries, the logical AND?
Andrew, I have a question. So I think, for example, if 1 means 16, because it's 4, like 2 in the power of 4 is 16, and the other one also is the below line is also 1. So that means if 4, like 16 plus 16 is 32. So I think it should be 2 at the power of 5. So it should be 1, but at the column ahead of that row. Is
Okay,
it the total?
So you've got to remember, right, that in the logical and, you're not really adding things together. You're kind of negating bits, right? So if you look at a binary of 50 over here, right, where you've got all zeros, 1 1 0 0 1 0, right? On the binary of 60, you've got a bunch of ones over here and you've got zeros. When you AND them, it's simply saying 0 and 0 is 0. 1 and 0 is 0, 0 and 1 is 0, 0 and 1 is 0, 1 and 1 is 1, 1 and 1 is 1. That is why you end up with this 48, because effectively these end bits end up being negated, because 0 and 1 will effectively end up as 0. So it's not it's not a normal kind of addition. It's a negation operation where only 1 and 1 is ever going to be 1. Does that make sense?
Yeah. Okay, sure. So it's not the sum. It is like a logical function.
Yeah. So then this is how a logical AND works, right? Now we're going to talk about a logical OR. So I'm going to go down here again, and it's going to change my comments here. So that we can just move this down.
While you're doing your commenting, presumably you'd use a logical AND when you're doing subnetting.
You would
as an example.
You would use a logical AND in particular where you're attempting to find what the beginning and end of a subnet is. So if you're doing networking, for example, and you've got 5.5.5.5/27, and you want to know where the beginning of the subnet is, you can do a logical AND against 27 bits of mask. It will chop off the remaining bits, and what you will be left with is the first IP in the subnet. And I can show you an example of that in a bit if you want.
Yeah.
An exclusive OR. So I've uncommented that. And we're going to look at an exclusive OR. Now, an exclusive OR, very similar to a logical AND, except that with an exclusive OR, 0 on an exclusive OR with 0 is going to be 0. 1 exclusive OR with 1 is also going to be 0. And the only time you're going to get a set bit is if 0 and 1. So basically your two bits are different. It will come out as true. So it's testing difference between your bits effectively. If the two bits are true, set a 1. If they are, two bits are different, set a 1. If they're not different, set a 0. Right? So if we run the same code again, showing the exclusive OR, what you'll see here is 0 and 0 over here come out as 0. 1 and 0 are different, so it sets a 1. On the next one, 0 and 1, they're different, set a 1. 0 and 1 are different, set a 1. The moment we get to 1 and 1 are both set a 0. So you end up with a completely different result because it's doing that test and putting stuff in there in that way. Does that make sense? Does the logic behind that make sense?
Yep.
Yes.
Okay, so that's called an exclusive OR. You'll see that in the code, a AND is just a single ampersand like that, the logical AND. An exclusive OR, it uses that thing there, the caret, to print that out. Sorry, to do the operation. So that's an exclusive OR. Now, the next one that we're going to talk about, and this is actually one that I use a lot more often, and you'll see why when I get to it. So let me just comment out my exclusive OR. and we'll do a logical OR. So on the logical OR, which we're going to talk about next, the logical OR basically says the result will be 1 if either of the bits will be 1, otherwise the result will be 0. So if it's a 1 and a 1, it comes out as a 1. If it's a 0 and a 1, it comes out as a 1. If it's a 0 and a 0, it'll come out as a 0, right? So if you look at this again, same thing, you will see that we get another completely different answer. 0 and 0 is 0, 0 and 1 is 1, 0 and 1 is 1, 1 and 1 is 1, etc. So that's what a logical OR does. That is simply a pipe sign, single pipe sign. Do not confuse that pipe sign with something like this. That basically is a normal OR within the context of the code. So that's saying if this is true or this is true. That is not the same as a single pipe, which is a logical OR. They do very different things, right? So be careful of that. So that does a logical OR. Now, this particular function here, as we go further down, I'll show you exactly why this is so useful. But before we get to that, so I just got asked from the Facebook group if there's a limit to calculate this kind of binary format in Go. Basically, 64-bit integers, there are functions in certain libraries to handle numbers far bigger than 64 bits long, where you start going into the big libraries which start handling 128-bit numbers. I don't think I've ever actually used them. It's rare when you see people who need numbers that large, and in the IPv6 world, we typically handle the v6 addresses in two parts, so 64-bit and 64-bit. Okay, so I've just seen.
So Andrew, would you like to take the question from Rajesh, where he asked about the real-time use cases of this, where you use it?
I'm going to get to that right after the next two functions.
Okay, sure.
Because the next two functions will cover something slightly different, and then we'll get to where this all comes into play. I will just notice that Danium in the Zoom chat said that when looking at logical operators, truth tables can be useful. And if you Google around, you can find truth tables which will show you kind of what these operators do. What I'll do is I will see if I can dig one out later. And oh, Danium actually pasted one. Thank you very much, Danium. I'm going to paste what he pasted into the other chat as well, so that you just open that so that everybody has got it. That also contains a couple of operators that we're not going to go through today, but that's a useful diagram. Thank you, Daniel, for that one. Now, the next thing that I want to talk about are when we start talking about. Let me just go down here. I'm going to uncomment this quickly. So comment that out, and we're going to talk about shifting numbers. So left shift. Now left shift and right shift do very similar things, just in the exact opposite direction. Effectively, if you look at, before I run this, if you look at a number like this, what happens when you left shift it is that it will drop the leftmost bit over here, add a bit over here, and move the whole number, the binary string, off to the left, right? That has the effect of doubling the number in question, because effectively you're going and saying move all your kind of least important bits to a higher importance position, so your low order becomes a higher order, and then you drop off your highest order bit at the end. If you look at this and I run this, you'll see that I've got the number 50 and I'm shifting it twice. So what's happened, let me just actually modify this slightly so that it's just nicely aligned so you can all see it. We'll just pad that nicely. There we go. So you'll see that I've shifted this by two bits, and this is the shift operator over here. That's the left shift operator, and it's saying shift number 1 by X number of bits, and it shifts it 2 places. So what you'll see here is this is the original. I've added 2 zeros over here, and everything else has simply moved to the left. And as a result, the first shift I doubled 50, the second shift I doubled the result of that, and I end up with 200. So effectively, I've now taken this and said, go ahead and double it twice over. Does that make sense to everybody?
Anyone? Any questions from the group?
Hey, what is the operator which is actually moving by 2? Can I show it? You have just put a 2 left.
It's this here.
Like, okay,
so it's simply those two. Those two. I can't remember what you call that thing.
Okay. Less than. So it is always 2. Suppose if it is like 3 means we have to add 3 left arrows?
No. This is an operator, right? These two are an operator. This is saying take number 1 and shift it left by the number of bits in number 2.
Oh,
so,
okay. You mentioned number 2 as 2. Okay, got it.
Yes. So, for example, if I passed in 4 over here, it would say shift number 1 by 4 bits, but I'm passing in 2 over here. Does that make sense?
Yeah, it makes sense now. Yeah.
And I can actually show you that. If I take this and I go down to the code over here, instead of passing in 2, I'll pass in 4. And you can see that over there, I've now shifted it by 4, and I end up with 800 as an answer because I've shifted it 4 bits. Make sense?
Yeah, definitely.
Okay, so now let me comment out that one and go to the right shift example. As I said, the right shift example is effectively the same thing, just the only difference is that we're shifting in the other direction. And we'll run that. And you can see here, what's happened here is that I've dropped off this 1 and 0. And that's an interesting result. I think that result is wrong. I will check that code in a second. But effectively, I dropped this 1 and the 0. I shifted everything to the right. I end up with this answer. Apologies for the bug in the code. I really should have checked that. Danium, any idea why I'm getting funny result there?
Taking a look now.
It's a bit weird. Because that should be equivalent to 1100, which should be in binary. Apologies, guys. sometimes mistakes happen.
Yeah, that's perfectly fine, Andrew. It's absolutely fine, no problem.
Because that should be a decimal of 12. Oh, I know why. It helps if I don't make that typo over there. Sorry. There we go. I just had the two numbers set as each other, and that wouldn't exactly work. So just a typo. Apologies. So you can see I shifted that there. 50 becomes 12. Effectively, what's happened here is on the first shift, it would have divided 50, right? And it would have divided it, end up with 25, divided again, you get to 12, because remember, I'm working with integers. There are no floating points, etc. here. So I end up with 12. It's a division. That makes sense.
Yeah, totally makes sense.
Yes, Andrew.
Okay, now we're going to start talking about where do we use this type of stuff. So if ever you get into network programming, for example, or various other types of programming, you will see that sometimes they will give you flags in the middle of a protocol that are made up of a bunch of binary bits. So it's not a single number. It's a bunch of this bit means this bit means this, true or false, within a single number. And that means that you're going to need to be able to test what those bits are, right? Is this bit set? Is this bit not set? So what I've got here in this next function, and before I run it, I'm just going to close it. This code looks a lot more complicated than it is. And I'm going to walk you through it. So please don't freak out and run away and log off at this point, because I promise you this is a lot simpler than what it looks like. Firstly, one of the things that I wanted when I wrote this test bit is keep in mind that if I'm testing the bit position of a number, I have to know how long is this number, because I'm going to be testing from bit 0, which is generally your highest order bit, on the most left-hand side of the number. That's what I qualify as bit 0. The right-hand side being your lowest order bit will be on the most right-hand side, right? That means that when I want to test in an 8-bit number what is on the most left-hand side, I have to shift the whole number by 7 bits, but I've got to know how much am I shifting by, right? To move that bit that is right on the other side all the way through to my lowest order bit on the right-hand side, right? So what I said here is I'm going to pass in a generic, what is called an interface type. Now, I also did this so that I can talk to you about interface types very briefly, and I will go into this in far more detail in future. But for now, what you need to know is an interface type is basically a generic container for a variable. You can have any type of variable in an interface type. It can be an int, it can be a uint8, it can be a uint16, it can be a string, it can be a pretty much anything, right? So this says take this generic input and take a number of bits that I want to test. So which bit do I want to test? And then I'm going to print something about this. And I'm saying here, I want to print number 1 as if it were a decimal, which is the %d again. I also want to print it in binary, which is the %08. Then I'm going to start doing a calculation. But notice something about this code. On this generic variable, number 1, I need to know what type of variable is this, because I'm going to be changing my calculation based on the different type of variable. So I use a switch statement. Switch statement is basically the equivalent of a case statement in another language, right? And I say switch on the type of this variable. And then I have case entries for each different variable type, as well as a default entry that says, well, I don't recognize this type, so go do something else. So that is how you pass in generic variables. You use the interface, then you switch the type, and then you've got a case statement doing things for the various types. Before we move on to the binary stuff, does everybody get that? Does it make sense?
Yes, Andrew.
I would like to have one more repeat on that. I missed something in.
Okay, so one more, yeah, so one more just to go over this again. This interface type is a generic type of variable. It can be virtually anything, and it's actually a container. An interface type can contain many, many things. So I can call this function, and I can pass into it an 8-bit integer, a 16-bit integer, a 32-bit integer, a 64-bit integer. Well, these are all unsigned integers, or pretty much anything else, right? When I get this variable in, the first thing I do is switch it, which is the equivalent of a case statement, to say, what type of variable is this? That's what this says. Switch on number 1 and switch on its type. So tell me about the type. Then I've got a case statement that says, is this a uint8? So is this an 8-bit integer? If it is, run this code here. If it's a 16-bit, run this code here. If it's a 32-bit, run this code here. If it's a 64-bit, run this code over here. If it's none of those, return an error. Make sense?
Got it.
Okay.
Thank you.
Now, just one note about switch statements within Golang. The switch statement terminates at the first match, basically. So if it matches this, it's not going to keep matching down. There are ways to do fall throughs, etc., but I'm not going to go into those today. We'll get to that at another point. But effectively, the moment it matches one of these, that's the end of it. Though in this particular case, I'm actually returning at the end of it, so that's irrelevant anyway, right?
Hey, Andrew, sorry to interrupt actually.
Yeah.
So when you say interface is a container, it can logically accept any type of variable, right? Can you just give one example and explain this to make like understanding easier? For example, if I am giving integer variable num1 as some kind of integer, right? So will that accept how this case will work? That will go to the default one in that case?
Okay, so I'm going to open up some Scratch code here, and I'll give you this in another demonstration. So we're going to create a function, test func. That's going to take in a variable. We're going to call this A, and it's an interface type. And now we're going to look at what that type is, right? So switch A dot type. Then I'm going to go case int. Now, we'll talk about this assertion at the end here in a second, right? I don't technically need to do this with print because print will figure this out. But when I start setting and working with A, I actually need to tell the thing what this is. And it's something that you've got to get right because you can actually crash stuff if you get it wrong. But for the purposes of this demo, A was a UN16. And the string so we have a function and a default Okay, so now if I call test func int a, sorry, int 10, or test func un1610, or test func, this is a test, which is a string, or test func and I've got a error here. Let me just see. Okay, this is fine. Remember, numbers by default are integers, so that's fine. Okay, so let's look at what I've got here, right? I've got this function, and this function takes in this generic type. And I'm then testing the type. If it's an integer, it's going to print it. If it's a UN16, it's going to print that. If it's a string, it's going to print that. If it's none of those, it's going to tell me it was an unknown type. So look at the code that I'm calling it with. This is going to pass it an integer. This is going to pass it a UN16. This is going to pass it a string. This is going to pass it a slice of integers, which is not going to match those types, right? Now, if I run this, you can see it over there. It's detected the type and it's acted on them differently. Does that make sense?
Yes, yes.
What I'll do is in the GitHub repo, I'll add some more code that explains this a little bit better. Does anybody have any other questions about this before we go on, or are we all clear on this? Because it's quite important to understanding that other code.
Andrew, Bala here.
Yeah.
What happens if we don't use interface the function type? So if I don't use interface, how does it work basically?
Okay, so if I take this and I say a as an int over here, right? Which is telling me that a is an integer, right? Let me just comment out the switch statement because you can't switch type on a non-interface, right? And actually, let me just comment out all of this. Okay, so that's going to print out a as if it were an integer, right? Because that's all my function accepts, right? But now look down over here. That is now an invalid function call because I can't pass in a UN16. This is an invalid function call. I can't pass in a string. This is an invalid function call. And if I try and run it, you'll see cannot use UN1610, type UN16 as type int in argument to test func. That is why you use interfaces where you need different variable types.
Okay, now I got it. Thanks, Andy.
And this goes back to what I said last week about Golang being a strictly typecasted language. It's very particular about your types passing into and out of functions and in various other situations. The types have to match. The interface is there to give you a way around that, but use it sparingly. You only use that where you really have to. In the case of the code that I was writing here, I wanted to be able to take in different types for the purposes of demonstration. I wouldn't say that it's a good idea in any way, shape, or form to simply use interfaces everywhere because they can cause you problems, right? If you look at this, so I'm going to take this back to an interface type again. And I'm going to uncomment this. So we're back at the original code here, right? Now, I've said if this is an integer, print this is an integer, and I'm asserting that this is an integer, right? But look at what happens if I get the assertion wrong. It just panicked. That's an instant crash. You've got to be careful with these things. Because if you get your assertions wrong, you can crash your code. Does that make sense?
Yes, Andrew, thanks. Got it now.
Perfect. So let's go back to this code over here. And we've said we're testing for the type. And we're saying if this is a uint8, because now we know that it's got 8 bits, we're going to print this line over here and we're going to fill it all in. And I'm going to walk through what I'm printing out here, right? If number 1, which is this integer over here, notice that I do not have to assert in a print. I only have to do that if I'm actually operating on the thing. So at the moment, I can just leave out that assertion over there. I say print the number 1 and print it again to give me the binary of it. Then print how many bits I'm shifting it by, 7 minus bit, because what I'm actually saying there is I want to see what the bit is on the other end of the number. Then I print out the result, right, is equal to that number shifted by 7 minus bit. Now, why 7 minus bit, right? Because it's an 8-bit number, and I want to know what the left-handmost bit is, right, from the bit that I'm specifying, because I count my bits from 0. So 0, 1, 2, 3, 4, 5. If I want to find out what bit 0 is, I want the bit 0, which is on the far left, moved all the way to the far right so that I can do a test on it, right? So let's just break this code down into multiple lines here quickly, make it a little bit more easy to read. There we go. Now, you'll see I'm double printing each of these variables because I'm printing it in decimal and binary. So that's why you see num1 and num1. Then I'm printing what I'm actually shifting to get. Then I'm printing the result of the shift. The final line here is where this gets slightly more interesting. Once I've shifted this number, right, just add a comma there because I've separated it onto another line. Once I've shifted this number all the way to the right-hand side, there'll only be one bit left from the original number. That's the bit that I've moved from the left to the right. What am I doing at the next step? I then AND it by 1, which will erase everything else in that number, and it'll do a logical AND of 1 and 1. If the result is 1, then that bit I was testing was set. If the result is not 1, it wasn't. So what does this look like in practice, right? Because I realized that this can be a bit of a mouthful to understand without good examples. So we'll just run that one. Just go back to that terminal window. You can see here that at the moment I'm shifting this 0 places, right? Because at the end of the day, I'm saying I'm testing bit 7. That's an 8-bit integer numbered from 0 to 7, right? So I'm shifting it 0 places. I'm going to end up with exactly the same number. And this bit here was not set. So I'm going to return false, right? But if I change this to take exactly the same number, and I'm going to actually print a bunch of these at the same time to make this easier to see. Let's look at this. This first one, the next one, I'm saying I want to test bit 6. Again, numbered from 0, bit 6 is this one over here. 0, 1, 2, 3, 4, 5, 6, 7, right? So I'm testing whether or not bit 6 is set. So what does it do? It shifts it by 1, which produces this, right? You can see the zero's been dropped, added at the other end. Then it does an AND over here. Over here, this AND, right? And what is it ANDing? Remember, 1 will be 0, 0, 0, 0, 0, 0, 0, 1. So it'll be an AND across that, and you'll end up with just that 1-bit set. If this is 1, guess what? That bit was set. If it's 0, it wasn't. And then return that result. Does that make sense to everybody? Or did I just really confuse everybody?
It's clear.
Any questions? I do.
Actually, it is going top of my head. Actually, I'm not able to follow you.
Okay.
Maybe Rajesh, what you do is after this, you rewatch this video, and then you can
Definitely,
yeah.
I try to understand, and I will contact Andy in maybe of this one offline, and then we'll see.
Yeah, I mean,
you can post the questions in the group if you come up with that.
Definitely.
Yes, I mean, I'm in the group. I'm on WhatsApp. You're welcome to, if it's not making sense, contact me and I'll work it through step by step by step. Just one other note about this. Daniel asked me about exception handling when you're using the interface type. Basically, what he's saying there is it a good idea to add exception handling? Yes, and exception handling basically says, is this a type I don't recognize? And you'll look at the end of this code. In my switch statement, I have a default entry. And that says, listen, return an error. I do not know what this type of integer is, so I'm not going to perform any of the above code. So in a switch statement, that default says, literally, this is my default if I don't know what it is, and it returns an error. Couple of other things to talk about in this function before we move on. This function has two return values, a Boolean value, which is true or false, and an error type. The error type is a built-in type, and it effectively allows you to return an error that can be a string, etc., that is identifiable. So what you'll see here is if I get to default, I return false because, well, Boolean has to return true or false. And then I return an error, which is created like that. And that error I can then read in my calling code to see what is this error that it returned, and I can print that out. In all of the other cases, you'll see that when I return, I'm returning the error as null. Because if I've got two returns here, I have to actually return two things. So the error value is filled in as a null value at the end of each of these returns. Does that make sense? I'm hoping it does.
Yep.
Okay. Now, one other thing as well. You'll notice that this return doesn't say if this is this, then return true, or if this is that, then return false. It simply contains a straight algorithm like that. Basically, what this says is, do this bit of math over here. If it's equal to 1, that's going to return true, so return true. If it's not, and this entire statement is false, it'll return false. So it's evaluating the statement to true or false, if that makes sense. I hope it does.
Yeah.
Now, the only difference between these 16, 32, 64 is, as I said, the number of bits that we're shifting by. Because to get, again, from that left-handmost bit to the right-handmost bit, I have to do a different size shift. That's why I divided this into different types. Does that make sense? I will say that this code is actually some of the more complex code you'll run into in terms of doing this stuff, because it's got all of the assertion and the shifting. So take your time, go through this, but don't let it scare you, because not all Golang code is this complicated, I promise you now. Right? But now, that's how you test bits in numbers, and there are a lot of practical applications for that. If you've got, for example, if you ever wanted to write a BGP protocol, or you wanted to write a network protocol, many of the network protocols contain different bits that are set in groups, and you have to be able to test the bit. That's why you need bit testing functions. The other major use, somebody asked me about the practical applications. I'm going to show you something else here, and this is a function that I created called our Voradic OR function. What this does is, remember above we've got the logical OR, which I said takes number, OR it by number, and it says that it'll be 1 if either of the bits were 1, otherwise the result is 0, right? So over here, I created this little function called Voradic OR. Now, what this function does is take in a number of integers. You'll see that this function has a slightly different definition where I've got that ... int. That basically says I can take a whole bunch of arguments in here so long as they're integers, and it'll just keep going 1, 2, 3, 4, 5, 6, right? What it actually does is it gets those as a slice. So if I return nothing, I'm going to have an empty slice of integers coming in here. If I put something in there, I'm going to have position 0, 1, 2, 3 to reference the arguments. That's how a Voradic works in Golang. But they all have to be the same type, and this has to be the last input argument within the function. So I cannot, for example, do something like that. That's not valid, because it's not going to know where this Voradic ends and where this starts. So I can do that. That's valid. It knows that b is one integer, so the first argument here is not part of the Voradic. Otherwise, the rest of it has to be Voradic. Does that make sense?
Yes, Andrew.
Okay. So now what do I do here? Once I've got this whole thing of integers, I'm going to create a slice. So just, that's purely for printing purposes. See, I got a question earlier, sorry, that I missed, about the differences between interfaces and structures. Totally different in many ways, and I'm going to come back to that question when we talk about functions, possibly next week, if you don't mind. Just remind me, but effectively, a structure contains a whole bunch of elements that you directly reference. An interface doesn't work in the same way. There are similarities and differences. If you want to have a more detailed discussion before next week about differences between interfaces and structures, let me know offline, we'll take it up. Otherwise, I'll take that up next week. But going back here on the string slice, I'm creating a slice of strings just so that I can print this all nicely when to show you what this does. Then I create another integer over here. We call that res for result. And we start iterating through our inputs. Remember I said that Voradics are effectively a slice. So I can range through this as if it were a slice. Now you'll see that I've got for I, comma in. I will reference the offset of the slice. So the first element of the slice I will be 0. The second element of the slice I will be 1, etc., etc., etc. The in is the actual value at that position in the slice, right? So effectively, if I've got something like this, input 0 equals 10, when I will be 0, in will be 10, be the value. That makes sense? So all I'm doing is basically iterating through my input arguments for my function here, right? First thing I'm doing, convert them to strings and stick them in my little string slice over here just for printing purposes. The next thing that I'm doing over here, this is the important part, is I'm taking the result and I'm doing an OR of that input value, right? So effectively, res is becoming a combination of the input values. Does that make sense?
Yes, yes, Andy.
Right. So let's look at what this actually produces, right? And it'll probably make more sense. And I'll show you where this is useful. Let me just, by the way, you'll notice at the moment I've got an error up here that's saying this won't compile. The reason is I've created a variable coming out of this function that I'm not using because it's commented out, but I'll print it over here. Just to make things happy again. So I fed into this function 1, 2, 4, 8, 16, and 32, right? What did it do? It took all of those numbers and it ORed them together to produce a number of 63 because it took all the binary values and it laid them one on top of each other, did its calculation, and came out with the number 63. Now, that makes sense?
Yes, yes.
Okay. Can anybody think where that would be useful before I continue? Any ideas?
IP address calculating, host bits.
Wouldn't really use it for that. Any other ideas?
Subnetting?
Think beyond networking. General application. Okay, let me show you. Right. So firstly, once we've created this integer, let me talk about isolating elements in that integer before we move to the next step, right? So you can see what that Voradic function does right over here, right? The next function in here, I created something called combined contains, right? What this function does, and again, I'm going to break this down just to make it easier to read. We'll print the first number, we'll print the second number, and then we'll print a logical and then we'll print a negated truth or false over here, and we'll return that truth or false, right? Let me enable that. And we'll enable the final piece of code. Watch what happens when I run this. So in my Voradic OR over here, right, I included 1, 2, 4, 8, 16, and 32, right? That gave me a number of 63. I want to see whether the number that results contains the binary equivalent of the number 4, which is this over here. So if I take this number and I AND it with this number over here, right, I should end up with this number over here. That tells me that 4 is part of that subset that is in there. If I do the same thing with 64, however, 64 ANDed with that is going to produce 0. It's not a part of it, right? So I can test whether or not specific numbers are actually part of another number by doing this. Does that make sense?
Yes.
Okay. Why is this useful? So let's write another little function here, right? We're going to call this our log function, right? And we're going to take a log type, and we're going to make the log type be a UN64 because we want 64 types of logs, right? Then in this log type, we're going to define a list of log types. In this case, I'm going to talk about map variables in another point, but let's define a bunch of log types, right? Okay, our first log type, right, is going to be the value of 1, and we're going to give this a, we're going to say that value 1 is going to have a string equivalent of equals. I got my syntax now. There we go. Log type 1 is going to be equal to test1. Log type 2 is going to be equal to test3. Log type 4. Now keep in mind, I'm doubling these each time, right? Because I'm effectively creating numbers that when I OR them are going to fit cleanly into the same number. So we'll go 1, 2, 4, and 8. So I've got 4 different log types over here, right? And then I'm going to pass in a message, which is going to be a string as well, right? And I'm going to say here format.printf. This is log type %s. Message is %s. And I'm going to tell it over here that I want to say this log types, right? Just trying to think of the exact syntax here. Well, the first thing I'll do is say that if log type, I'm just trying to think of the exact syntax of this. Hold on half a second. Sorry, I'm going blank here for a second. It happens. Sorry, I'm just looking at my other screen here. So over here, we've got this nice little log type function over here. What I will say is that I want to print test1, test2, test4, test8, right? Then the first thing I want to do is to say, is this log type a valid type, right? So my combined log type over here, valid log types, is going to be 1 or 2 or 4 or 8. So that's now the combined, right? If my valid log types ended with my log type is equal to 0, which means that this is not a valid log type, return, do nothing. Let me just see, and I've got to make this a UN64, by the way. You'll also notice here that it didn't like that because, sorry, wrong one. these variables have to be the same type. Here we go. So if that's 0, the log type I've passed in here is not valid. It's not part of my valid log types, right? If, however, it is valid, right, then I can know very clearly that I can simply say that I'm going to print my log type by saying something like, that should be right. So what this does here effectively is now created 4 different log types. When I call this, if I pass in 1 over here, it's going to print test1. If I pass in 2, it's going to print test2. If I pass in 4, it's going to pass in test4, etc. Effectively, I managed to take one variable, one simple UN64 over here, and make it reference 4 entirely different things because I'm referencing the binary structures underneath it to do that. Does that make sense? Or have I completely lost everybody here?
Yeah, can you explain one more time?
Okay, so log type over here that I'm passing in, right, is going to be a number, right? And what I've done here is I've taken all the valid types. So these are the valid types. I've got, in this case, 4 valid types. And the actual better way to, if you really wanted to express this in a way that may be slightly easier to understand what I'm doing here, is remember 1 is going to be your first bit, right? Your right-handmost bit. So that 1 statement is fine. 2 is going to have your second bit set. So if I take 1 and I shift it 1, I've now got 2, right? If I take 1 and I shift it 2, that's going to be 4. If I shift it 3, that's going to be 8. That's why I'm doubling it, right? Because I'm creating a binary string that is testing against those various bits for validity. So each time I put something in here as a reference, I double the number, I take the binary value, and that's what I'm looking for, right? That makes sense?
Yep.
Then what am I doing down over here? I'm saying, is this type that I've passed in here part of the combined number that I've got over here? If it's not, this isn't valid. Therefore, I'm going to do nothing. I'm just going to bail on this function. However, if it is part of that, then I'm going to print the message that is in that map at that offset point with the message that I passed in. So one number, 4 completely different types. Does that make sense?
Yes.
Yep.
I think there are going to be a lot of people who are going to be studying this video for many hours. But guys, what I've taken you through here now, I was going to see if we could move on to other functions and stuff today, but I think at this point, we've been going for about an hour and 40 minutes. So I think I'm going to leave it here for today. And next week we will talk about functions and the rest of it. I'm not going to set a coding challenge this week. What I am going to say is that for everybody on here, take the code that I've given you here. It's on the GitHub URL. And go through the video. Study the code. If you don't understand anything, you can get me on Facebook. You can get me on WhatsApp. Come and talk to me until you do understand it, because this is going to get really important as we move deeper and deeper and deeper. And this is also fundamental to understanding programming, because keep in mind, the computer thinks in zeros and ones. Everything that you pass into the computer is a 0 or a 1, right? It doesn't think in terms of strings of text, etc. It thinks in zeros and ones. And if you don't understand how a computer is dealing with the zeros and ones, the moment that you want to go deeper into code, or you want to start doing performance optimizations, etc., you will not have the grasp to do that. This is absolutely fundamental to how a computer works. So I really need to stress, you guys need to go through this video. If you don't understand anything, go through it function by function. Come and ask. Post a question on the Facebook group. Post, ask me on WhatsApp, whichever. If you're asking on WhatsApp, please put the question into the group. There are absolutely no stupid questions, only stupid answers, of which I'm sure that I can find plenty of. But there are no stupid questions. And I will also take that question, I will post it onto Facebook along with the answer, so that the answer, everybody gets it. I know that this has been quite a probably exhausting session, and I've given you guys a lot to think about. I hope that you've learned something. I hope I haven't lost you all. But please, as I say, just ask. Oh, I got another question in here that says the line that shows result as performing 1, 2, 4, 8, 32 equals 63. Yes. So that line of code over here, is done over here. Basically, because it's doing it in a loop, right? I'm ORing the last number in the loop to res each time. That's why as I feed in 1, 2, 4, 8, etc., each time I do that, I simply OR the result with that, and I'm effectively adding it to the end by setting those bits. I hope that makes sense. I also got a question about whether or not this is like an enum data type. Not exactly. Daniel, how would you respond to that question about the enums?
So I think in terms of enums, membership is quite explicit, and it's more abstract, right? Because it may not actually be part of the underlying binary. It could be essentially anything, where this is more closely tied to the low-level binary.
Yeah, I would agree with that definition. I was trying to find you. You see, you've got such an eloquent way of wording things. But yeah, I hope I've taught you guys something. As I said, I realize this was quite a heavy session. I hope that the next session, where I start talking about all the function types and function methods, etc., may get slightly easier, but I can't promise. And after that, we're going to start talking about pointers, and then things probably definitely won't be easier. Well, depends on how you view pointers. But study this, because knowing this stuff, as I said, is really fundamental to how a computer works, and it can be helpful. You will see as we move forward more and more practical applications for this as well. So yeah, that is the session for the day. Has anybody got any other questions, comments, thoughts, anything else that I can assist with before we call it for the day?
Andrew, thank you for this wonderful session. All of the people who are in the group in this session, as well as on YouTube and Facebook, they are going to take this as a medicine. Morning one time, afternoon one time, evening one time. Okay, 3 times they are going to watch this 1 hour, 40 minutes video, whether you are on the bed or you are anywhere, and they're going to do this for 1 week completely. And this is for your benefit. You completely watch, rewatch, ask questions, as Andrew said. Andrew is so nice. He does not mind answering questions, and he is almost like 24/7. I can see, irrespective of which part of the world you are. So thank you, Andrew.
I don't sleep much. What can I say?
When you say medicine, Joe, is that medicine for the Joe virus?
No, this medicine is for this particular video. They have to watch every day 3 times for the next 3 days, so that they get it. And if I don't get questions in the group, then I will be chasing after them after 3 days.
I will also say, Perry, I will also say, to Joe. Joe, you owe me
Yep.
some prime code.
Yep.
And furthermore,
Absolutely.
and furthermore, right, just because you're
Yep.
making everybody else's life difficult, I want to see from you, this is just for you, I want to
Yep.
see a piece of code that makes practical application out of some of what I've taught today before next week from you.
Yeah, sure. I take that. I will.
There's the
I will.
challenge. Perry,
Yep.
you get the challenge for next week.
Oh man.
Okay.
My problem is time, that's all.
Now, is there anyone in this group so far who have joined who are not part of our WhatsApp group and who came from the LinkedIn? If you are, and I saw some of you have filled our sheet, I will be sending you the group link where Andrew is part of us, where we constantly talk, discuss, everything goes on there. So is there anyone who is not part? Then let me know in this chat channel. I will send the link.
Yeah, I think
if
what
you
you
have
can
joined.
do, Joe, is give me the exact link offline. I will post it onto the
Yep.
Facebook group as well, so that people can find it from the Facebook group.
Sure, I will do that, Andrew.
And then I will also paste that into anybody who's also reading this. We're going to try for next week as well to further expand the streaming. So I'll be streaming on LinkedIn as well. But I'll also paste the link that Joe's going to give me on the LinkedIn comment where I talked about this session. But hopefully by next week we'll be streaming to YouTube, Facebook, and LinkedIn to make this even more interesting, and get the wider audience.
Absolutely, absolutely.
Any other comments, thoughts, anything else before we close?
Anyone want to say anything? Let me see. 27 from here. How many in the YouTube and Facebook, Perry?
We have a total of 16 between them. So another 16 there.
Okay.
And
Okay.
please, guys, invite your friends. I will post the 2 videos that were on Facebook before this to the YouTube channel as well, so that all the videos are both on YouTube and Facebook. So, share the channel, let people come and learn from it, and hopefully everybody gets some benefit out of it.
Absolutely, absolutely, Andrew. And then thank you for helping us, for helping this community across the globe. You won't find this kind of information in anywhere, nowhere in the internet. This level of the lowest level of code with so much of patience, with almost like 2 hours.
Always a pleasure, and I will see you guys next week.
Thank you, guys. It's a
Okay.
wrap.
Thank you, Andrew. Thank you, Perry.
Thanks, guys. Cheers.
Thanks, Andrew. Thank you, everyone.
Thank you.